All right, today's lesson, right, will be on superposition. It will not be the usual kind of superposition lesson, right, whereby I'm just going to teach everything from scratch. Okay, I do going to help you recap most concepts. But what I want to do also, right, is to address a lot of problems that you may have, questions that you may have in your head that you are just too shy to ask, don't know how to ask whatsoever. Okay, so along the way, right, if you manage to have questions, most of the time I ask who have question, nobody have question. But if you have questions, right, please ask. Okay, because it's really useful. The questions that you ask, right, someone else may have the same problem, but just they don't know how to ask, or they are just too shy. So when you ask, you're actually contributing. Okay. Without further ado, right, let's begin. You can refer to the handout that I sent you. Let me share my screen. This thing, right, cannot replace practice. So after we had the session, you should still go on, right, and do some questions. Yeah. Perhaps, right, you can try the MCQ if last year you haven't tried it. Okay. Or last year you tried it and you found that you forgot most of the things. That will be a low cost way to help you recap, because MCQ is relatively fast to do. Yeah. And always, right, keep some things on hand. Like when you go out, right, on the bus, you can just take out do 10 questions, 5 questions, better than nothing. Okay, let's start. Superposition, right? This topic is difficult, okay, for many reasons. I think most of all, right, it is very hard to visualize. Yeah, because, right, wave most of the time can't be seen, except when you are talking about water wave in a ripple tank. It's straightforward and you can see it. But in the case of light wave, sound wave, right, we don't see them. I mean, we experience them, but we don't see superposition taking place. And because we don't pay attention to them also in our daily life, and conditions may not be there for us to observe them, therefore, right, we don't have much experience with them. So you'll feel that this whole thing, right, is pretty abstract. Okay. We have to live with that, because, right, they are just not very easy to perceive. Hang on, let me close my door. Okay. And it all starts, right, with the principle of superposition. This definition, right, I believe most of you are sort of familiar, but always will miss out some things. And each of the ingredient, right, as with all principles, all carry significance on. They contribute to build up the meaning of something. For instance, right, when you talk about conservation of linear momentum, also is in the absence of a net external force, total momentum of a system. You see, a lot of information there already. First, right, tell you a condition or no net external force. Then next, right, is all you state, what are you studying? Is a system or closed system. And a closed system, what property will it have? Is total momentum. This physical quantity, right, will be conserved. Not anything else, not KE, not this, not that. Yeah. So you see, all these definitions actually contain a lot of things. But unfortunately, right, we don't appreciate them. We simply, right, treat them as a 1 mark thing, right, to memorize so that we can get 1 mark. Okay. That's disrespect. Yeah. So let's respect the principles, because this is the only thing, right, that is called principle in this entire topic. Surely it must be damn important, yeah, because it set the foundation for everything else. So first and foremost, right, it states that when 2 or more waves overlap, okay, and it must be of the same kind, okay. So you see a few things already. First thing, right, is same kind overlap. Then something will happen. What is that thing happening? Is superposition. Then what does this law, right, tell you? It tells you how to find the resultant. So the resultant at any point, right, at any instant is given by the vector sum of the individual displacement at that point, at that instant. Okay. Yeah. So and that begs a question, right? Superposition is not just about those convenient things that you remember, like, oh, superposition means constructive interference, destructive interference, so on. Those are observable patterns. But superposition, right, could take place even without all these observable patterns being there. Because right, it's always taking place on, as long as you have more than one wave. But why don't we see this kind of superposition effects, right? Because we need to understand, if you want a permanent pattern to be there, there needs to be the right condition to be present. Okay, then you can observe that pattern. Now, a while later, a while later, a while later. Because when you observe, right, it takes time. Because it takes time to register this phenomenon in your mind, right? So it must have the same pattern, right, remaining fixed for a while. Then you can see a pattern. Yeah. So this thing, right, is very, very broad. It's just telling you, right, this is the only one rule, okay, to predict what will happen. Okay. Let's go on. The superposition, right? Let's zoom out so that we have an overview. Today, right, we are just doing a few portion of superposition, which is two source, okay, and two source, right, under this subset, okay, there's item inside called double slit, okay, and part of the double slit, right, problem is also related to diffraction grating. So diffraction grating is just a multi-source. So you understand two source in general, then you go on to understand one particular special case, which is double slit, and double slit is for light, okay. Then you extrapolate this understanding, right, to multiple slit, also for light. Then you will understand grating. So that's their big picture relation, okay, and they are all related in similar way. Yeah. So let's go on, right, to the simple two source scenario. This one, right, this is a diagram that you see in every set of lecture notes. Okay. I actually don't want to say too much here. It tells you, oh, when it phase, then when the path difference is 0.5 lambda, what will happen? You will have disruptive interference. So the resultant amplitude would be a difference. When they are in phase and path difference equals to full lambda, and you have a phase difference due to this of this amount, so they will be in phase and amplitude will add up, and you call this constructive interference. But this is not too good, okay, because right, it's like telling you too specific already, okay, like so many conditions. So whenever we do things, right, we want to generalize, okay. So we simply saying, right, these two chunks of things, right, they contain two categories of information. First category of information, right, is the information about source, okay, or whether they are in phase or not, I circle. This is about source. Second piece of information, right, is about path. Okay, and path contribute also path phase difference. So essentially, right, what we want to generalize into, right, is in the end, what causes two waves to constructively or destructively or anyhow interfere depends on phase difference. Yeah, and phase difference, right, contributed by two accounts. One account is called source, and one account is called path. Yeah. So in all problems to do with two source, we really need to remind ourselves, right, that we need to look at both contributions. Okay. And why is in the first place, right? I didn't say, right, why when the phase difference is 2 pi or 4 pi, you will get constructive. Then you need to go back again, right, to understand what are waves made up of, because superposition is about more than one wave overlapping, right, and causing disturbance. So we say, what is a wave about? A wave, right, is about disturbance in a periodic manner. Someone at the source, right, is vibrating, okay, and it's always true. This statement is always true. You may think that, hey, I don't see the thing that's vibrating. Yeah, often, right, we fail to see that connection. For instance, right, you see a filament bulb, right, you say, hey, who is vibrating? Who is vibrating to give out the light wave? It is the atoms, right, within the filament, okay, they are very energetic because the temperature is very hot. They're very energetic. They vibrate more vigorously than normal. The energy, right, that they distribute out to the surrounding is in the form of light. So it is the vibration, right, of the atoms, right, that gives out light wave. Similarly, for sound wave, maybe it's your diaphragm, maybe it's the speaker, the sound producing part, whatever that's called. There's some vibration. It disturbs, right, its surrounding. And see, go back to that source, right? What is the source doing? The source is simply doing some SHM. SHM, right, at the source leads to the surrounding particles also vibrating, also doing SHM, and they disturb down the chain. So you form a wave. So at any point, right, whereby you have a wave arriving, the particle is trying to vibrate, okay, because someone is disturbing it. Yeah, it's vibrating. And right, if there are more than one waves arriving, right, means, right, there are more than one set of instruction telling the particle to vibrate. Okay, one wave will carry one set of instruction, and that instruction, right, got two parts to it. First part, right, is the amplitude. Okay, I'm telling you, vibrate with this amplitude. Okay, and another guy is also telling you, vibrate with this amplitude. If, right, we happen to tell you this vibrating with this amplitude, right, and we tell you, right, vibrate with this particular phase. If we are telling you the same thing, telling you go up, okay, at the same time, right, then you will go up, and you'll do, right, what we both tell you, and you add up the amplitude, and that's called in phase. If, right, one person tell you go up, the other person tell you go down, then you confuse. You'll do, right, whoever you follow the net result of whoever is louder, yeah, whoever is more dominant. For example, right, your father say, I go out, go out and play lah. Your mom says, no, stay home and study. Or your mom win, okay. But then because your mom met some resistance from father, right, so the instruction is less powerful, yeah. So that's really what is constructive and disruptive interference about. There are two instructions arriving, telling the particle what to do, okay. And superposition, right, is the basis for this. What happens in the end, right, is summing up the two set of instruction. The instruction come in the form of displacement. Yeah. Here, right, with just that, we are going to dive in, right, into a simple example, okay. Because, right, with this example, you will learn a lot. And because you're not hearing superposition for the first time, I don't want to elaborate too much, right, unnecessarily. Yeah. So let's look at this example. I hope you have this file with you so you can refer to the question. First couple of parts, right, I'll just go through very fast because they are relatively easy. So we have this particular setup, okay. I also want you to learn how to appreciate the setup. Later I'll say again. See, we have two sources, X and Y, emitted sound wave, okay, and wavelength is 0.4. Notice, right, wavelength is 0.4. The gap between them is 7, okay. They're just one order of magnitude away, not far, okay, not far away. And that is always the case. You wouldn't have, right, the sources and the order of magnitude of the wave, right, being very far apart. Why so? Very hard to detect the constructive disruptive interference. So they first tell you, right, that the wave emit, the sources emit wave of equal amplitude, each of A. Find the amplitude at R, okay. You already know, right, that the sources are in antiphase. R is where the distance, right, is the same or equidistance. Yeah. Do you see my writing, right, lagging, or do you see it quite live?
I think it's okay.
It's okay, right? What about my talking?
Yeah, it's okay also.
It's okay, sorry, because I just need to check. The last time I used this, right, there's a bit of lag. Yeah, so therefore, right, we go back to the formula. We really want to know is there any phase difference, right, contributed by path and source. Yeah. So here, right, we know source, right, contribute already got a pi, or path contributes 0 because it's equidistance. Therefore, right, you have a pi phase difference. So destructive interference, resultant A 0. Okay. What about for Q? For Q, right, this is where, right, for this kind of problem, you always need to physically draw out, right, the path that the wave takes to go there. Then you can see, oh, one path longer than the other. Yeah, path difference is just a difference in the length. So you do the Pythagoras theorem, you get 1 meter as a difference, and you relate it back to the wavelength, 0.4 meter. Oh, so this is 2.5 wavelength. Therefore, right, you say, ask yourself this question again. So path and source, right, who contribute how much? This time round, right, path contribute pi. Source, let's say source contribute pi. Path also contribute pi. So end up, right, you get 2 pi. So the wave arrive in phase. Yeah. So you get constructive interference. Yup. With that, right, then the next part they will ask you, right, this is a very popular question in this kind of scenario, right, what the detector will detect when it moves from R to Q. Okay, so let's zoom in. We already know, right, that R here, oh, where's my pencil bowl? Let me make it thinner. Yeah, at this point, right, we have the path difference of 0. Okay, so the path difference is 0. At this point, right, you know path difference, right, is equals to 2.5 lambda. Sorry, the words are not turning out too well. I think it's because it's too zoom in already. It's not picking up my writing. Yep, never mind. So for all the points in between, right, so you can deduce that at some point, right, higher than R, you will have a point whereby it's path difference of 0.5 lambda, then 1 lambda, then 1.5 lambda, 2 lambda, 2.5 lambda at Q. Okay. Therefore, right, you will correspond to positions of constructive, destructive, constructive, destructive. Okay. Excluding R and Q, they are all together, right, 2 sets of constructive and destructive interference pairs. Yeah. Therefore, you will detect, right, 2 series of loud sound followed by soft sound because you start off with the destructive. So you get constructive, then destructive, then constructive, then destructive. So 2 pair, 1 pair, 2 pair. And be quite clear here. Don't go and say bright, dark. Okay, people talk about sound. You talk about bright, dark. Where got how do you bright, dark sound? Okay. Similarly, right, when it's talking about light, you don't go and loud, soft. Okay. Yeah. Next up, okay. You see, that is not the only way, right, that you can move the detector. You can also move the detector, right, like along X and Y. So that's part C. Suppose, right, the detector is moved from X to Y at a constant speed 1.0. Calculate the rate at which the loudness fluctuate. Yeah. So this is where, right, things get really interesting already, because, right, it really tests how you see path. Yeah. So see, the detector is somewhere along X and Y. So let's just take it as a point A here. So at the beginning, right, let's consider we have a spot whereby it's a soft sound. Okay. How I know? Random one. Just say there's one particular point whereby it's a soft sound. So when that is the case, right, what do we expect? Okay. because right, the wave are in anti-phase, right, and it's soft sound, this means that disruptive interference. So the path difference, right, will be n lambda. N lambda will contribute a path difference, right, due to the path, phase difference to the path, right, of 0, ma. Okay. And so due to the source, you have a pi, so end up disruptive. So at point A, right, you have a soft sound. Suppose, right, you let the detector move, okay, to the next position whereby you have the softer sound again, and that will be point B. So what will point B be? So you consider, right, this distance that the detector move is called x. Yeah. In terms of YA and XA, right, YB and XB will simply be YA minus X and XA plus X. Yeah. Essentially, right, it gives you the same thing as before, which is here, but minus 2x. Meaning, right, whenever you move by a distance of x in this particular setup, the path difference actually changed by 2x. We are not saying that the path difference is 2x. I'm saying, right, the path difference from first scenario changed to the second scenario by 2x. Yeah, because one path got longer by x, one path got shorter by x. So the path difference changed by 2x. And 2x, right, will just nice be equals to 1 lambda. Because, right, that is going from one soft sound spot to the next soft sound spot. Yeah, so that's going from a particular n lambda to a particular n plus 1 lambda or n minus 1 lambda. So path difference will have changed by 1 lambda, and path difference is also equals to 2x. So, seems like confusing. Therefore, right, 2x, right, will be equals to lambda. Okay, so you can figure out that x is equals to 0.2. Is that okay? Anyone confused? If this is the first time you're working through something like this, right, you're bound to feel a bit uncomfortable, overwhelmed. Look at it a few more times and try it out yourself. Now, right, we know, solve to solve, right, the distance is 0.2. Okay. And right, this detector is like moving down at 1.0 meter per second. Okay. And so, right, 1 second, you will have moved by 1 meter. And just nice, right, you will have covered like 5 sets of those soft to soft, okay? Meaning, right, you will have gone through 5 fluctuations of loud sound to soft sound, loud sound to soft sound. So 5 cycles, okay? And you actually don't need to write cycle. You can simply write 5 per second. Also can. Write cycle or not, doesn't matter. The unit here is per second because you're talking about a particular frequency. Okay, I hope, right, this example warms you up enough to appreciate and apply, right, whatever that we just talked about. If you have appreciated whatever that we have just talked about, right, you can be quite sure that this pattern of thinking, right, actually applies for everything. You actually don't want to keep on, right, by pure brute force, right, exposed to many situations. Not possible, because, right, everything, physics, right, is always can change one. We can always adapt to a new situation, come up with a new problem for you to solve. And you can't bulldoze and try to know everything. You can only develop a method of thinking inside your head. With this method of thinking, right, if it's robust enough, you can solve all problems in similar manner. Okay. Sorry, I accidentally exited the thing. Let's enter it again. Any question at this point while we are waiting for this to load? Okay, like I say, right, I'm going to use this session to talk about a lot of the hidden things, right, that you may not have noticed in the past, but I hope, right, now you notice and you appreciate them better in the future. So one of the things, right, that I want to bring your attention to, right, you see, two-source problem, right, can be coming in all sorts of forms. One of the difference, right, that you can see, right, is the setup itself, right, may vary in scale by a great deal. Okay, some could be in terms of mm. Okay, some could be in terms of meters. Some could be in terms of kilometers. Yeah, and why can they vary so much? The reason is because, right, you see, superposition is a phenomenon, right, that can be observed in waves. And waves, right, are so varied. You have on one end, right, super low wavelength, on the other end, super high wavelength. So different wavelength, right, will demonstrate, right, the phenomenon of superposition in observable interference pattern, right, more in different kind of scales. Yeah. So if you're talking about a radio wave, right, you will see the setup, right? Radio wave is like meters. You see the setup being in hundreds of meters, kilometers. If you see microwave, you will expect something like mm. Okay, so your setup will be in cm or at most a meter. Yeah, that is the logic. Sound is more have a spread, but generally, right, sound is also between something like cm to meters. Yeah. So there is one variation that you see in questions. Why is it like that? Okay. The second variation, right, is the setup could be really, really weird. Okay. Sometimes, right, you can't even associate it with a two source kind of situation. For example, just now this one, right, you see, how is like a satellite, right, moving in orbit, a two source problem. And in fact, right, this one you need to use the double slit equation. Oh, you see, we tell you, right, double slit equation is for two slit, but yet, right, this is for two sources of radio wave on Earth's surface for satellite. Why is it that to solve this problem you need to use the y equals to, y equals to n lambda L over D formula? Oh, doesn't make sense, right? You see, you're supposed to be using this only for double slit. Why here also can? Reason because the conditions are similar. And what are the conditions? So you see, you cannot just, right, memorize things and get by one. You need to understand, right, the conditions behind it. Okay, if the conditions met, then the rule can apply. If the conditions not met, then cannot. Okay. So I was saying, right, the setup could be really different. Okay. For example, this Kunst tube. Okay. Where do you see the two paths? One is obviously like here. Okay, they meet here. At the exit point. The other one, right, is like going the other way. And because, right, this tube you can shift it left and right. Okay, for one of the branch, so you can change the length of the path. So you can vary the path, and you can get varying path difference. So you can get, right, a certain path difference. Conditions are right, they contribute plus a source, right. Here we have no phase difference at the source because, right, it's one source. Yeah, so only the path is contributing phase difference. So when the path difference is equals to wave lambda, for example, 2 lambda, 3 lambda, you get constructive. You see, same thing applies. And the skill is what? Is to appreciate the setup. Sometimes, right, it's the sources that move. Sometimes it's the detector that move. Sometimes the setup, right, changes, like this case. Okay, so what you want to do is always identify the path, then form the equation relating the path to whatever that you are given. Okay, and solve whatever that you are required to. And in the end, right, you're bound to use this one. Okay, just now, right at the beginning, I said, right, there are times, right, that we, or rather, there are often times that we don't observe interference, which is the reason, right? The reason behind which is because the conditions to have observable interference pattern, right, are very specific. These conditions, when not met, right, we simply won't observe them. Okay, so what are they? Number one, and you must distinguish. These are two sets of conditions. First set, right, is when will superposition occur? Given in the principle already, must be same kind, okay, and overlap. So this is the first thing that must happen. Yeah, you see, to fall in love, right, or to become enemy, you must be at the same place at the same time, know each other first. Or if you don't reach this, you never met each other before, you simply won't become friends or you won't become enemies. Next, right, for observable pattern, observable, right, implies that it's permanent, or at least, right, it is slightly more permanent than not. Okay, that means it stays for a while. You can see it. So the same spot will be constructive interference, right, now and a while later and a while later and a while later. Then you can notice, this spot is constructive interference, or it's bright, it's loud, it's high intensity, whatever. And then the neighboring one is not, and the neighboring one is, and so on. Then you see pattern. That's called a pattern. One spot is not a pattern, but many spots, right, alternating is a pattern. So these positions, right, of where the high and low intensity occur cannot change. Then you can see it as observable. Okay. So first condition, right, is that sources must be coherent. Yeah. Because, right, if the sources and coherent means what? Constant phase difference between them. They don't need to be in phase or in anti-phase. We can just use a simple diagram, right, to illustrate this. Without going into too much details, right, about double slit, I'll just use this illustration. Suppose, right, you have a source here. Okay, and you see the screen, right, is like here. You expect, right, that the center, right, will be a bright fringe. Okay, so you expect here to be a constructive interference CI. But, right, you see the light, right, light source is not symmetrically put in between the two slit. So one path is like sort of longer. So by the time, right, the light reach here, right, between this point and this point, right, the vibrations that comes out of the slit, right, got a phase difference already. So this phase difference, right, as long as it's consistent, as long as it's constant, then it doesn't matter, because, right, the path will compensate. You'll know that, oh, okay, just now, right, you took a longer path, never mind, now I sacrifice a bit, or we'll meet here. So this turns out to be the new zeroth order. Yeah, and okay, can. So you will have your pattern appearing. It's just, right, that the whole pattern shifted by a little bit, offset by a little bit. That's all. Is it still observable? Still observable. Okay. So what matters, right, is the constancy of the phase difference, not whether they are in phase or must be in anti-phase. That's too draconian. Okay. As long as they are constant, can already. And constant means what? Constant with respect to time. Now and later, still the same value. Approximately same amplitude. Why is this important? This point, right, you can think about it as, right, that's for contrast. If you want to see bright dark of loud soft, right, the two waves arriving, right, the constructive and destructive interference, right, must be obvious enough with respect to each other. Suppose, right, we have a let's give you an example. Let's say you have A and A, okay? Yeah, constructive interference, right, will give you 2A. Destructive interference will give you 0, okay? If you have, let's say, 1.5A and 0.5A, constructive interference will still give you 2A. Destructive interference, right, will give you how much? 1A. Yeah. So, but we don't compare just the amplitude. We want to convert it into intensity. So, if A is corresponding to I, this will correspond to 4I, and this will correspond to 0. 2A is still 4I, and A, right, becomes only or becomes I. So now you can see between 4I and 0, right, contrast is stronger compared to between 4I and I. Yeah. So the more similar their amplitude, the more contrasting the intensity of constructive and destructive interference positions. Okay. And that will mean that it will be observable because contrast is good. Lastly, right, if you're talking about transverse wave, okay, they must be unpolarized. Unpolarized means what? Means, right, the sources, or if you look at the polarization, you see, in terms of diagram, right, we always draw this kind of arrow. If both are unpolarized, right, means both are contain polarization of any direction. Both sources also have waves, right, polarized in any plane. Therefore, right, when they meet, wave of one plane can always find wave of the same plane, okay, the particular wave of the same plane from the other wave to constructively interfere or destructively interfere. And everyone can find their matching same polarization partner. Yeah. So unpolarized, good. If not, right, then they must share the same plane of polarization. So if I am vertically polarized for the top slit, bottom slit must be vertically polarized. Yeah. If you have top slit is vertically polarized, bottom slit will be and bottom slit is horizontally polarized, right? You will end up getting a smudge of pattern. You will get a smudge. You will not get any bright up, bright up, bright up. Okay. Why so? Yeah. This one I scared, right? Some of you, your foundation not very strong, right? You get confused. Let's just suppose, right? We have two waves. And for the first wave, right, we'll call it up as positive. Okay. And the second wave, right, we call it right as positive. So you see they are differently polarized. So if you add these two waves, right, or what will you get? You'll get diagonal or 2A. Yeah, this A and this A. So at this position, okay, that will be the outcome. But then, right, if you have the first one as up, which is positive, the second one, right, according to its convention, is negative. So it's like these two are supposed to be out of phase. Yeah. But right, you see, you plus together, right, you'll simply get like that, which is 2A as well. And in terms of amplitude, right, this is 4I, this is also 4I. No difference. So you see, in these two cases, right, one case is both are in phase, the other case is in anti-phase, but no meaning. Whether the two, if they are perpendicularly polarized, right, with respect to each other, in phase and in anti-phase, they undergo constructive or destructive interference, right? Outcome is the same amplitude. So you get no observable pattern. Okay. This one, right, if you hear it for the first time, you'll be confused. You need to absorb it one. Okay, you need to appreciate more. even after today, maybe you try and understand it again, you may still not, because right, your foundation still not, doesn't allow you, conditions are not there yet. Or maybe right, a few months later, you may appreciate it better. Okay, let's go on, right? So with all this, right, we actually have enough tools, right, to appreciate even deeper. Okay, so now, right, let's go to this scenario of so we are going to build towards two source interference of light. Okay, eventually, and that's double slit. Yeah, but before we go there, right, let's just look in greater details, right, what is happening. Okay, so we use a simple diagram, right, which is like this. This could be a ripple tank, or these are red and blue lines, right? They are wave fronts, crest and trough. Crest and trough, you use it for water or for ripples. For other waves, right, you just say it's a wave front. You don't need to say crest is what, trough is what. No need one. So just say it's a wave front. They can be a ripple tank waves, or they could be something else. They could be anything, or it's the same. So we can think about them as ripple tank for now. Okay, and let's imagine, right, that the solid line are the crest, dotted line are the trough. So whenever crest meet crest, right, we will have constructive interference, and therefore, right, you have the amplitude add together. Okay, so along the blue lines is where all the crest meet crest, trough meet trough. So you connect them, so you get the blue line, and you have constructive interference at these positions. When crest meet trough and trough meet crest, they always fight. Okay, and you have destructive interference. So that is the pink line. So pink line, we have a name. It's called a node. Okay, and all the N words, right, all are like meaning nothing one. Okay, now or NA, none. Okay, you see all these are saying don't have, 没有. Okay, so the blue one are anti-node. So these are anti-nodal line and nodal line. Yeah, but then, right, if we were to, let's say, study them, right, along this line, we draw a cross section through this medium, and we study the intensity, right, of the resultant wave along the cross section. What do we expect, right, if let's take one step back. If there was no superposition, what do we expect? Okay, so let's study, right, what will each of the wave give us. If there was no superposition, right, and there was just one wave at first, we expect, right, at this position here, the wave intensity, right, will be something like this, or your peak at the direct straight through position, or then it falls off the other way. Then for the other one, right, it's probably going to be similar, or it's likely to peak here and falls off the other way. So if you don't have superposition, right, you may expect, right, the intensity to simply add up, because, right, you have two set of wave coming, and with each wave, right, there's a distribution of energy along that line. Yeah, because some part of the line, right, is shorter distance from the wave, or you see from here to here is like shorter distance, right, compared to here. So that's why, right, the intensity vary. Yeah, and since, right, each of the pink and blue line give you the spread of energy of each of the source, right, if there's no superposition, right, you expect that the energy, right, will just stack up. Okay, and be like this. But in reality, right, we already know that superposition exists. So, right, it's causing the energy to be sort of redistributed. Okay, such that, right, you see, follow the nodal line and anti-nodal line, right, you know that it's actually something like this. I'm not drawing to scale. If you would like to, right, you can like use these lines to guide you. I think I draw too many. Let me erase them. Let me draw them better. So I have a node here, okay, and so on. And you can complete the diagram for the other side. Yeah. So you see, it's like there's some mechanism there, right, that is telling the energy. Some place you can land, some place you cannot land. Huh? Yeah. Some place can land, some place cannot land. And that's simply right, a very marvelous thing about it. How you think about it. Somehow there were some ways, right, that the two waves can communicate to each other, come out into an agreement, right, as to where they will park their energy. They will not park them anywhere, or they will just park them in alternate car park slot. Okay, you see a car park slot, right, one whole row, many slot. But they don't, the car somehow, right, have a 默契. Okay, 默契 is what in English? I don't know. Okay, some understanding. So they park alternate slots, something like that. And this diagram, right, is the people tank one. Okay, but right, I urge you to go and watch this. This comes from Veritasium. Okay, you can watch it, right, and you search for double slit experiment. Yeah, it's pretty interesting. So you can see, right, these are the wave, right, on the water surface. Yeah, and you can see, right, that there is no two set of concentric circle already. There's only, right, one set of pattern, because superposition is already taking place. Once they overlap, superposition will take place. You see, these are the nodal line or nodal line. Yeah. And antinodal line is where you see the undulation, because, right, crest trough, the amplitude double. Yeah. Yep. And with that, right, we'll head into double slit. Okay. You see, here we learn one more new thing. We learn, right, how to draw intensity against a cross section. Yeah, where the wave land. Yeah. Or you need to imagine, right, or let's say it got something, right, to capture the energy at that line, along that line, right, and you can measure the energy that arrive. So that will be the intensity along that line. Now comes to the last part, quite a huge part, okay, which is about double slit, Young's double slit. Oh, the things are a bit distorted here. Never mind. So how does the experimental setup, just in case, right? Yeah, you forgot already. So Young double slit, right? You see the setup, right? Looks like this. And once again, right? See, we would expect, right, from a very traditional way of thinking, right? Is light goes through each slit, right? Will generally, right, end up landing at one spot, right? Light go through another slit, will end up landing at another spot, right? So by right, you should see like, oh, got two spots only, but no, due to superposition taking place, right, they have the two set of ways, right, have a way to come to agreement where we can land, where we cannot land. Yeah, such that, right, if you put a screen there for the light to land, then, right, this understanding will be displayed to you. Oh, is this very difficult to understand? The two set of ways, right, has a set of understanding to know, right, where they should position themselves, the energy, where they are not supposed to. And that understanding, right, is backed by a mechanism called phase difference. Yeah, and we talk about that for the past 45 minutes already. Yeah, so end up, right, we don't see just two spots belonging to the two slit. We see, right, a pattern, or a pattern. Okay, that's number one. Next, right, we want to start off double slit, right, by critiquing, right, why the setup is terrible. Then, right, we'll move on to deriving, right, the mathematics. Why is the setup terrible, and why, right, it prevents people from understanding this whole thing properly? It is, right, to do with the way it appear in your textbook, okay, in your lecture notes. Here, right, we see, let's see whether I can move this diagram a bit. Okay, this is a typical double slit setup. Yeah, the top one with the light blue. This is so terrible for one reason, because, right, this is not how it looks like. Okay, the bottom one, right, that says closer to actual proportion, this is somewhat closer. Okay, yet, right, this is still not what it looks like. This is still some one order of magnitude away. Yeah, and these two, right, in relation to each other, it's just like my photo. You are like distorting, you're stretching it too much in one direction, compressing it too much in the other. So, right, it gives you a very distorted view. Okay. Let's look at this diagram here. We have three angles here for you to compare. In your mind, right, as you see this diagram, you'll tell me these three angles, right, are not the same. Okay. Why do you think they are not the same? Because, right, they don't look the same on this diagram. They look at different angle. Yeah, and this is your typical double slit setup. I'm telling you, right, that they are really the same. Okay, because a real setup, right, looks like this. Okay, so that is what, right, the distortion is doing to our mind. When you keep on seeing this setup, you can't appreciate, right, why are we saying that the angle is just the same angle. You don't need to care whether it's a top line or the bottom line, they are the same angle. Yeah, because they are truly the same. Why so? Because, right, you see, when you stretch this diagram, right, a lot more, this is the maximum I can stretch it already. But can you see, right, if I hide part of this diagram, right, and you can just see the red lines here, all this almost parallel. Yeah, almost parallel. And if this proportion, right, is like real proportion, they are parallel. Okay. Next question, right? Weird question before we do the math, right? Is why do the wave overlap in the first place? Because we know they need to overlap, right, in order to have interference, right? Why do they overlap? Shouldn't the light, right, just like go straight through and head out of the two slits, right, and head straight to the screen? Why would they overlap? They do. If you look from the top view, right, this is closer to what is happening. Yeah, we are just zooming into a region, right, close the slit, zoom in until we see the two slits in this manner. Here, right, got one phenomenon. Okay, it's called diffraction. So the wave, right, come out of the slit already spreaded. That's why they will overlap. And throughout the whole space, right, between the slits and the screen, right, most of it, they are overlapping already. Yeah, because the slit is pretty small. So the degree that the light of diffract, right, is pretty huge. Also, you'll spread out, right, fan out in this manner, and they will overlap. Why do we always draw only two lines? Because what we are trying to do is to study, right, what happened at a particular point on the screen. And particularly, right, we want to study what happened, right, where we see bright fringes. Because we do an experiment already. And we got, bright up. So we want to ask, right, why at the point is bright? So from where the point is bright, right, we draw two lines back to the slit. So see, that's a narrative. We already done it and we saw it
and we trying to work backwards and figure out the mechanism. That's why, right, we always draw these two lines. They are not the only ways. They are not the only paths. They are just the paths that arrive at a point that we are studying. Because, right, there are millions and uncountable number of paths, right, existing. A lot of combinations arriving at different points. And there are so many ways, okay? I mean, so many different paths, right, associated with this. Yeah. What about what's happening in the space in between? Well, superposition is also taking place. As long as they overlap, there's superposition. Then you say, hey, why we don't talk about bright fringe and dark fringe there? For practical reason, you never put a screen there for the light to fall on. If light never fall on a screen, right, what's there for you to observe? Yeah, you also don't see light, right, in a space in a room right now. You see your floor, you see your wall, you don't see space. Yeah, sort of. Correct or not? You see objects, right, because light landed there and part of it reflect to your eyes, so you know or you perceive that is something. But in the space throughout, right, there's always superposition. It's just we never study it. We study what happened at the screen. And now let's study, right, what happens at the screen. Suppose we have a particular bright spot, okay? And we already done this experiment. We saw many bright spots. And this bright spot is the n bright spot, okay? And this n bright spot falls on the wall. And because it falls on the screen, okay? And it's on the flat screen, right? I can give it a position is a distance y away from the center. Yeah. Then, right, I can first, right, look at this entire setup and give a description already. I can say tangent theta is equals to y over L. Why can I say that? Because, right, you look at the setup lah. The screen is distance L away. The bright fringe, n bright fringe is distance y away from the center of the screen. So the angle subtended by the line, right, coming from slit to the point will be an angle theta. Tangent theta equals to y over L. So this is the first thing that we can say before we even study any further. Next thing you can say, right, is let's zoom into the slits. You see, these two slits, right, carries wave arriving at a point which is bright. So we know, right, that these two paths, right, will have a particular phase difference, okay, that gives rise to constructive interference. So this path difference, right, has to be equals to n lambda. Okay, you see, and by the way, why is this the path difference? Because, right, you see, eventually these two lines, they go far enough, they converge. The bottom path, right, travel a bit longer. By how much? By the amount, right? This amount, okay. Because after which, right, the two paths will be identical already. So if any difference were to arise, right, it arose from the beginning, this extra bit, or at least, right, we perceive it at here. This is easy to relate to other things. And this path difference, right, leading to a bright fringe must be equals to n lambda. Okay. And we see this triangle, right? We can also do the geometry of this triangle. We know that this is angle theta. So n lambda over d will be sine theta. So this is the second equation we can write. Okay. And right, now we are going to do a small angle approximation. When angle is small, when theta is small, then sine theta equals to tangent theta. Some of you may not be too comfortable with this. Not too difficult. Let's draw a triangle to prove to ourselves. Okay. Suppose, right, this is a right angle triangle. Okay. And this angle is really small. I mean, we can go smaller, but I can't draw it. So you see, the adjacent and the hypotenuse about the same length. So opposite divided by adjacent and opposite divided by hypotenuse, right, is about the same thing. So sine is equal to tangent. Okay. And if that's the case, right, we can combine equation 1 and equation 2. So n lambda over d will be equals to y upon L. Sorry, I'm starting to lag already. And we can work out, right, the formula y equals to n lambda L over d. Okay. And if you want to talk about the distance between adjacent slit, you'll be the delta y. And you don't have the n anymore. It's just lambda L over d. Now, right, we'll explain, right, why is it that we use small angle approximation. There's a practical reason, okay? And the reason is because, right, you look at the triangle drawn at the slit, we have this relationship, sine theta equals to n lambda over d. This guy here is typically around 10 to the power of minus 3 meter. Sorry. Lambda, right, is for visible light. It's 4 to 7 times 10 to the power of minus 7 meter. Okay. Therefore, right, you can see when you take lambda divided by d, right, you'll get a really small number. You don't say, what if n is 1 million? Don't have 1 million one. Okay. For double slit, right, by the 10th bright fringe, right, the energy is already very weak. Okay. So you can see 10 bright fringe very good for you already. Yeah. So we're talking about like a small n, like 1 to 20, that kind. But then you see lambda over d is really, really small. Therefore, the theta are all very small. That's for double slit. And you may ask, right, why in diffraction grating this cannot apply? Typically in diffraction grating, right, lambda is still the same, but the d is much smaller, around 10 to the power of minus 6 to 10 to the power of minus 5 meter. So see, now, right, they are like just one order apart between wavelength of light and the slit separation. Okay. Just a quick mention. This is for monochromatic light on the left. Okay, we see that you see for red light, which have a largest lambda, the bright fringe, right, are like slightly further away. Okay, because from the formula, you know, n lambda L over d, or delta y equals to lambda L over d. The gap is bigger between bright fringes for larger wavelength. But you see only one color, and very neat. If the light is not monochromatic, right, for example, you use white light, then you'll see dirty patterns like this. Central band, right, is still white. Okay, no problem. First order, right, still okay. Second order and third order, right, will start to mesh up already. Why? Because, right, you look at the formula, right, n lambda L over d. There's a n times of L, n times of the lambda, okay, coming into effect. The largest wavelength of light, right, and the smallest wavelength of light is almost 2 times. That means, right, you can have 2 times of the smallest wavelength is equals to 1 times of the largest wavelength. So where you have the first order longest wavelength, you will have at the same position, right, the second order shortest wavelength. So they will overlap, or eventually, right, they will start to get very messy. So the first order, right, is always a rainbow for white light. Then the second order onwards, right, will be overlap already. So you can't describe it easily. Okay. We're done with double slit, and now, right, let's ask a question, right? What if we have 3 slit, 4 slit, 5 slits, so and many slits? So this diagram, right, show you what is happening. And you can see, right, very clearly, right, that when you have many slits, right, you actually have many peaks, right, See, 2 slits to 3 slits, you have 1 peak, right, being hidden, very small. To 4 slits, right, you have 2 peaks hidden. 5 slits, you have 3 peaks hidden. You have many slits, you have many small peaks, right, hidden. And if you have, right, a huge number of slits that you can't really count already, it's like uncountable level, then, right, all these small little peaks, right, they become so muted, like they don't ever exist. It's just like, right, if you have a tree or grow out in the grassland, you'll see the tree. You won't notice the grass are there. You won't see, oh, the grass got height. No, you'll see the height of the tree. Yeah. So in effect, right, when you have diffraction grating, you'll see like this kind of very distinct drop off, right? Very high contrast. Then in between one bright fringe and the next bright fringe, right? Nothing really. Okay. It's like one tree to the next tree, right? On the desert. In between is nothing. Yeah. Oh, got sand, got grass, but you don't mention that. Whereas, right, this one or the double slit one is like is a gradual variation. Yeah. But right, is there a difference between their math? Actually, no. Okay. Now, right, let's look at the setup and understand why no. Suppose, right, you have here, right, at point P is a bright fringe. Okay. So once again, right, we want to study, right, what caused bright fringe to occur. So we study it at the source, and I included this diagram here to show you that when you zoom in enough, okay, to the source, right, the right hand side is what you will see. Oh, the lines appear almost parallel again. And our scale here is still super distorted. The left diagram is still super distorted. In reality, right, for diffraction grating, your slit separation, right, is 10 to the power of -5. It's even smaller than what 1 pixel on this screen can represent. Okay, so it's like that small. So imagine the lines, right, going from slits which are that close, arriving at the screen, right, and then you zoom in, they are perfect parallel lines. No question about it. Oh, because, right, you hear this, right, you'll feel how can parallel lines meet? Yeah, almost parallel. Okay, approaching the limit. Oh, just a little bit less parallel than parallel. They will meet already, right? So you think about that case. And compared to all other type of lines, they are parallel. Oh, compared to non-parallel lines, they are parallel. So let's see, right? Suppose, right, we have one slit and the next, right? This one slit and the next. What if, right, we open up an angle here? This angle that open up here, right, is called theta, such that, right, the opposite side or the path difference is called lambda. Then things get similar to just now, because, right, this is exactly the condition for a constructive interference. And for this method, right, I should have called this, you can relabel on the diagram. Instead of calling it lambda, you can call it n lambda. The next one, you call it 2n, 3n, 4n lambda. So see, if, right, slit 1 and slit 2 have a path difference of n lambda, that allow them to constructively interfere. Then slit 2 and slit 3, right, will also have a path difference of n lambda. So 2 and 3 will also constructively interfere, which means, right, 1 and 3 will also constructively interfere because they will have a difference of 2n lambda. But who cares? As long as the integer lambda can already, and so on and so forth. So, right, in order for all of them to constructively interfere, right, you don't need to consider all of the slits. You just need to consider, right, whether 2 adjacent slits, right, can fulfill the condition or not. And the condition for 2 adjacent slits, isn't it just double slit? So this formula applies to 2 adjacent slits, and it applies for all slits. And this is the diffraction grating equation. Full stop. Okay. Is there any simplification? The small angle approximation don't have. Okay. Because typically, right, lambda is much smaller than lambda is just a bit smaller than the d. Okay, just a bit. Still, right, in some questions, there could be a change in the condition. Okay, you still have diffraction grating, but yet, right, we can actually use something similar to double slit equation. The reason for so, right, is because in those questions, the D is much larger. Okay, what is serving as a diffraction grating, right, could be something that is not the industrially made professional grating. It could be, right, a piece of cloth with a two-dimensional mesh. Yeah, you've seen those kind of questions before, right? So why is it that we can use the double slit equation, the y equals to n lambda L over d? It's because, right, the D for those meshes of cloth, right, fabric is large. It's not a commercial laser cut diffraction grating where the D is very small. Okay. When D is very small, right, we will end up getting theta which are large. Because, right, let's say this is 10 to the power of minus 7. Yeah. And this 10 to the power of minus 6. Then n equals to 1, n equals to 2, n equals to 3 will bring the ratio, right, quite huge already, close to 1. Yeah, maybe by n equals to 4, you get this number is like 0.9 already. Oh, so is it almost exceed the limit that you can have for the theta, which is 90 degrees. Therefore, right, in diffraction grating experiment, we expect the theta to be very large. Okay, for a normal grating that is like 10 to the power of minus 5, 10 to the power of minus 6 meters. So we do not use a flat screen to draw the rays anymore, or the position of the bright fringe. Instead, we either use a curved screen, or in experiment, right, we use a telescope on a spectrometer. Okay, so this is like a spectrometer. Telescope is where you observe, you put your eye there, literally letting the bright fringe land on your eye. Okay, so you see it directly, and you can traverse it 90 degrees to each side of the principal axis, so and see the whole thing. In a diagram, right, you will want to draw something like this. Light goes through, and you have a curved screen, and first order, second order, so on. Okay, 0, 1, 2 on one side, 1, 2 on the other side. Okay. With that, right, I come to the end of this summary for the topic. Yep. And I'll open the floor for question. Any question?
Mr. Greg, can you please explain the if superposition didn't exist part again? Because like if superposition doesn't exist, right, then how come like the wave can still add up?
Oh, okay. Is it this part?
Yeah.
Yeah, is it the if superposition don't exist, right? You see, we look at the individual blue and pink graph, right? They are just how the energy will have spreaded on the screen. Yeah, or just any imaginary line, yeah, cross section. For one wave alone and the other wave alone. Okay, so you switch off one wave, switch off the other wave. So that's the energy distribution that you collect at the screen. If you switch on both, right, a traditional interpretation, right, will be maybe you just add up the energy, yeah. And anyway, right, that's pretty logical, right? So because you expect, right, if you shine a light bulb, you have a light bulb in the room, or you install it on the ceiling, and you install a second light bulb or on the ceiling, you expect the room to be just like doubly bright, right? And it's like smooth, It's like smooth. It's a smooth spread of brightness. Yeah, it's like a gradual spread. But right, because of superposition, there is no such smooth slope. Instead, right, it is alternating pockets. Some part have, some part don't have, some part have, some part don't have. Why so? Because at certain positions, wave coming from one source and wave coming from the other source constructively interfere or disruptively interfere, and so on. So that is what that causes, right? Those alternate car park, or some alternate car park cannot park, okay, to exist. But yet, right, in our real life, we go into a room, let's say we have two lights, we switch on both light, right? We don't see fringes appear on the floor, okay? Not because superposition don't exist, it's because, right, conditions for observable pattern don't exist. Firstly, right, the two sources, right, are not coherent internally. When you are talking about say your ceiling lights, right? The ceiling light is huge, like it's like let's say the LED type inside maybe got 7 or 8 LED, maybe more than that, 10 plus, or small LED combined together. So each of those are one source, and within the source, right, is also huge. So you can't really say that they are point sources which are in phase, because one part of a LED and the other part of the LED, right, they may have they are not coherent. Let's put it this way. Yeah. And one light and the other light also not coherent. Moreover, right, if you have understood the logic of how far the sources are and what is the effect of the gap between the sources on the fringe separation, you'll see, right, that when you're talking about two lights on the ceiling, which are like 1 meter apart or many meter apart, the sources are too far already for you to see those gaps in the fringe. You see, you just think about double slit and versus grating. For double slit, right, we get very close fringes. That's when, right, the slits are far relative terms. When you have the slits being very close, right, like in diffraction grating, you'll see, right, the fringes spread out. They'll become further. But yet, right, for two light on the ceiling, right, it's like many thousands of times, right, worse than the double slit case. Double slit, right, you only see the bright out, right, being millimeters apart. Now, right, if you make the sources, right, meters apart, you'll see, right, the bright out appearing like maybe like 10 to the power -7, 10 to the power -8 meters apart. So you see nothing already. Okay. Even if they should exist, they wouldn't to your eyes. But in the first place, they wouldn't also, because the sources are not coherent. Okay. And which is why, right, they need to use double slit. Why need to use slit? Because, right, light has a very small wavelength. So when you use even a light bulb, right, different part of the light bulb are not coherent to each other. So you need to pass the you need to put a slit in front of a light bulb, so that, right, only one narrow section, right, of the light coming out of the light bulb that can pass through the slit arrive there. So this particular segment of light, right, that can arrive at the slit and goes out of it, right, is almost like a point source. Okay. And if it is like a point source, then, right, it will have internal coherence. If it's not a point source, right, different part will have different phase difference with each other, and that phase difference may change over time. So internally, they are not coherent, which is why we never talk about those kind of complicated source. It's always, right, a point source and simplified. Yeah. I deviate too much from your question already. You're just asking, right, why if superposition don't exist? It's just be a adding up of the energy. And why do we expect that? Because, right, energy is just like a scalar. Scalar, right, in normal sense, right, we simply just add them up. We don't expect any difference here.
Oh, okay. Thank you.
Please ask all your weirdest question, all the questions that you find disturbing. Or I already show you an example. I asked a lot of weird questions already. These are real questions that I have inside my head, not fake one. It's not I asked to pretend that I don't know. These are really questions that I don't know last time.
Mr. Clark, can I explain why, right? There are different observations for like double slits. Because for Young's double slit, you're assuming that there's negligible slit width, right? Then why is this observation different for double slits with finite slit width?
Oh, the difference in the slit width, right, will cause number one, the brightness of the fringes to be different. But if the slit separation is kept the same, right, then the fringe separation is also the same, because you look at the y equals to delta y equals to lambda L over d, as long as the d is the same. So by the way, right, I should clarify to the rest who may not understand your question. So Curtin is asking, right, normally, right, we will say that the slit, right, is so small, we don't consider the size. So what if the slit is like bigger, okay, but they are still the same distance apart, or distance compared to where, like the center of the slit now. So this like still kept as d. The difference, right, is that the fringes will be brighter, because more light pass through, your opening is bigger. Another difference, right, is your envelope size will change. Okay, but I don't want to talk about that. That is the single slit diffraction effect. You see in this diagram, right, you see this envelope, right? This is affected by how big the slit size is. Okay, how big the opening is. Nothing to do with the D. Okay, it's everything to do with what we call sometimes we label this as A. I think in most of your notes it's labeled as B. Doesn't matter. Yeah. So Curtin, you're asking what? How will it affect, right? So envelope will change, brightness will change.
Okay.
These are the two things that will change.
So for point sources, for point sources there is no like diffraction envelope, right? Is there?
Point sources if you push to the extreme, then no.
Okay.
Actually not no lah. You just you'll not see the minima. The envelope will be so wide that you don't see minima.
Okay, thank you.
But we don't need to go there, because in our syllabus we want to see the envelope appear. Any other question from everyone else? If not, thanks for being here. Have a good evening. And for those of you interested to attend the gravitational potential rerun, see you tomorrow. Bye-bye.
Thanks, Mr. Clark.
Thank you, Mr. Quack.
Thank you, Mr. Quirk.
Thanks, Mr. Quack.